Welcome back friends for another lecture on quantum field theory and quantum entanglement. So, we were continuing the quantization of the Dirac fields, and then we in the last lecture we did after the quantization we started going into the interaction picture, and we showed that the interaction picture just borrows from the interaction picture which we developed for the bosonic field theory, and then you just go ahead, except that wherever you define the contractions you have to define it with anticommutators for the fermions. That is the only difference between the bosonic Wick theorem and the fermionic Wick theorem, where the commutators are replaced by the anticommutators. So, today we will continue with the fermionic interactions. So, the first simple example which we did was fix the Lagrangian of the Yukawa theory. So, we wrote down the Lagrangian for the Yukawa theory, and then we computed psi-psi to psi-psi scattering purely from Wick interaction, Dyson series and Wick theorem. Okay. So, to revise a little bit more, so let us look at L Yukawa. So, this contains as I said L kg, L Dirac plus L interaction, where L kg is the Lagrangian for the Klein-Gordon field, which is given by del mu phi. Let us assume a real scale Klein-Gordon field, and then we introduce mu by 2 square. So, this is phi square essentially, and mu is the mass of the scalar field. And then we have the standard Dirac Lagrangian psi bar I del slash minus m psi, and then you have the interaction field which is y psi bar phi. Now, this is psi bar del slash psi m is the Dirac interaction Lagrangian, m is the mass of the Dirac fermion, and phi is the mediator for the Yukawa interactions. Now, you can, instead of doing the Wick's theorem, okay, instead of doing the process, so the process we looked at is essentially psi-psi going to psi-psi. We will like to do the same thing with respect to with using Feynman rules essentially. So, let us derive the write down the Feynman rules. For this interacting Lagrangian. So, what we have, so you have an okay, the Klein-Gordon thing is very straightforward. If you have an incoming scalar, it will, or external scalar with a momentum p, it will just pick up the phase essentially into the vertex. It will just pick up 1 essentially, or and e power I minus ipx if it is a particle. If it will pick up a e power minus I plus ipx if it is an antiparticle. Okay, the particle is given by this, and the antiparticle is given by the opposite direction. But here we are dealing with the real scalars, so they do not really have particle and antiparticle, there is only one scalar field. So, we can remove the other part essentially. So, the particle and antiparticle do not have any sense in this case, because there is only one real scalar field. Now, we have to do the same thing, and then there is a propagator of the scalars. So, this is given by I if it has a incoming momentum p square minus m square plus I epsilon. This is the Feynman propagator between this is reflected by these two vertices and a dashed line in between. This is the propagator, this is the Feynman propagator. Now we have to write the same things also for the fermionic field and also for the for fermionic field and also for the interaction vertex. So let us start writing for the fermionic field. So for the psi incoming psi particle, so it will pick up the external lines. Essentially let us write down the external lines first. So incoming particle to the vertex with a momentum p and a spin r, say for example, okay, then you pick up, you write a spinor u p of s, and outgoing particle okay. Now an outgoing particle, say let us write it in this manner, outgoing particle with a momentum p. So this would be u bar of p with a spin s. Similarly an incoming antiparticle, so you remember the signs of the antiparticle and the particle are interchanged. So for a fermion we typically introduce a solid line. So we have a solid line. So the incoming antiparticle is given by V bar Ps, and an outgoing antiparticle picks up the spinor V of s, P of V, P of s. See this carefully, you have an incoming particle which is given by u P of s and an incoming antiparticle. See, this is the vertex and the antiparticle is coming inside, see the direction of the momentum, but the charge is opposite in direction because of the Feynman-Stackelberg interpretation that for antiparticles you define them as particles travelling backward in time. Okay. So the charges, all the quantum numbers gets reversed, so the relative charge gets reversed. So that is the reason why you give in the opposite direction of the arrow for the antiparticle. So incoming antiparticle will have particle will have an arrow showing the direction of the incoming charge, whereas the antiparticle, incoming antiparticle will have the direction of the charge on the line reversed, essentially it has the line reversed. Okay, good. Then you have the fermionic propagator which we derived, and we will write the Feynman propagator I p slash plus m p square plus minus m square plus I epsilon. Now for the scalar propagator we have defined the mass to be mu. So just to make a difference between these two, so we will put mu square essentially. So this gives you the Feynman rules. Then there is one thing which we have still missed, and that is the vertex essentially. So that is the vertex. So the vertex here is this part. Okay. So this part you have a scalar coming in, scalar going out, a fermion coming in, fermion going out, and there is a scalar. Essentially the scalar is does not have any direction, it is not a charge scalar. This will pick up a coefficient minus Iy. So, this is psi phi essentially. Okay. So, this is the vertex. So, given this vertex, the external lines, the internal lines. Now, all this we have derived it just from the Lagrangian essentially, we have not done anything else. Okay. And with this let us compute some simple process. Okay. So, this process let us take some examples, let us compute. So, we do the same, first let us do the same process, which is psi going to psi. Essentially it means that you can have nucleon, so nucleon scattering through a pion essentially. You can think example would be nucleon scattering through a pion. So, this is the relevant physics example. So, you have psi going into psi. Now, for doing this let us first write down the Feynman diagrams. So, we had to think about all possible combinations because it is a 2 to 2 process. There are basically the S, T and U channels of momenta exchange. So, what you do is S channel is not possible here. Okay, you have psi, let us assign a momenta. Okay, psi. So, let us do our standard thing. So, P1 incoming P2, P1 prime, P2 prime. This is exchanging through a the scalar essentially. So, this channel is nothing but your T channel process. Okay. This is your T channel process. Now, you can ask whether there will be I said there will not be an what do you call S channel process. Why? Because if you okay, because it is psi, it is not psi bar. Okay. If there is a psi bar, then you can think of an S channel process, but you are dealing with like psi. Okay. So, that is the reason why you only have T channel process. There is also another diagram in which the outside the outgoing momenta can be exchanged essentially. Okay. So, you can have the same thing essentially. So, you have P1 prime, P2. Okay. Okay. So, you have psi and the phi is exchanged. This is called a U channel process. Now, let us see the momenta exchanged here. In this case, the momenta exchanged of by the boson, this Q. In this case, the momenta exchange is P1 prime, Q is equal to Q P1 prime minus P1. In this case, the Q is equal to P2 prime minus P1. Okay. So, the momenta exchange are different. Now, we can write down the amplitude, okay, and write down the amplitude and it will turn out to be, okay, let us assign this amplitude. So, you can write it down explicitly. So, you will have u of p 1 coming in, and then there is this vertex essentially which is minus I y, then you have the outgoing u. So, that gives me u bar p 1 prime. So, let me write it down as, okay, I have to put in okay. So, u bar p 1 prime times s spin s times u of p 1 dot r, okay, times there is the propagator which is, okay, let me write down the propagator in a second. So, then you have the second term which is essentially again p 2 prime u bar p 2 prime, okay, s prime dot u of p 2 r prime, okay. Then you have the propagator. So, this is diagram 1. So, this diagram 1 is p 1 prime minus p 1 whole square minus mu square times minus I y whole square. So, the amplitude of the diagram 1 is, and you can go back and check with the notation of the previous class essentially, and you will find it exactly the same as the amplitude as the previous one. Now, because you exchange the final states essentially you pick up a minus sign between the two relative amplitudes between T and S channels. So, the U channel amplitude, so diagram 2, okay. So, you will see that it is exactly the same as what we derived using the Wick theorem and Wick contractions essentially. So, you have again u bar of p 2 prime s prime dot u of p 1 dot r u bar of p 1 prime dot s dot u of p 2 r bar r prime, okay. So, you see that okay, very good essentially. So, you get this notation and then you divide it with p 2 prime minus p 1 square minus mu square, and there is a relative sign between these two diagrams because fermions are exchanged. So, this gives me the amplitude much simpler, much faster compared to what we got it from using the notation of say for example, the Wick theorem notation and Wick diagram notation and so on. So, with this, so the total amplitude is diagram 1 plus diagram 2 is the same except the notation is different. notation of the momentum assignments as what we have derived from Dyson series and Wick's contractions and notations. Okay. So, this is the Feynman method is essentially the easiest method, and we can use it, and then of course, you can have the differential cross section which we have seen in terms of is equal to mod I m square, and then there is the d omega essentially the phase space factor, which will help you essentially to calculate the differential factor, and there is also this delta power 4, the whole thing essentially, which is the momentum conservation. Which tells you the momentum conservation. So, which is here essentially P 1 plus P 2 minus P 3 minus P 4 P 1 prime minus P 2 prime. So, this will be P 1 plus P 2 minus P 1 P 2 prime minus P 1 prime. Okay. So, this should be always be imposed essentially, that it always conserves the energy momentum conservation law. Now, this is not the only thing we can do. Now that we have the Lagrangian and we have the Feynman rules, you can start applying it for not just this process. Okay. We can think of many other processes. You can think of all possible processes which you can think of, you can make from this Lagrangian. So, what all the other process the Lagrangian does predict essentially. Now, you can also think of the process like nucleon to meson. So, what I mean by that is you have something like psi psi, good psi psi bar go to phi phi. Okay, psi psi bar going to phi phi. Now, this will give me a bunch of diagrams. Okay. So, let us draw the diagrams directly. So, you can think of an S channel process something like this. Like this. Okay. This is an S channel. So, this is also a T channel process. Example same like this thing, this is a phi phi. So, if we assign momenta P 1, P 2 as psi psi to phi phi, right, P 1 prime, P 2 prime, and this is a Q, and this Q will be equal to P 1 prime minus P. Now, then again you can exchange these two momenta, the external momenta. So, you have the other channel, which is what we did in the previous class also, in this class, in the previous process also, P 1 P 2 psi psi P 1 prime P 2 prime phi phi. This is Q, Cu channel, and Q here is P 2 prime minus P 1 square. Okay. Q square is this, and from here you can write down the amplitude, and so you have nucleon going into pion. Essentially, you can think of this process as nucleon going into pion. Now you can ask the question, what about now when I am okay, one important point I missed to, when I am drawing this Feynman diagrams, I should always mention what is my time direction essentially. Okay. So far I have been taking the time direction to be like this, essentially these are the incoming particles, so the time is here. So in this case also this is the time is in this direction. Okay. Okay. So nucleon to pion pair. Now so we dealt with the T and U channels in both the cases essentially. So whenever you draw a Feynman diagram, you have to mention what is the direction of your time. So because you need to know which are the incoming particles from which. Okay, that is the reason why we because if you change, if there is a possibility that you can think the time to be vertical, and then this direction the diagrams will have a completely different meaning, because we are looking at channels of momentum exchange. So what happens is an S channel will look like a T channel if the time direction is not, so there will be some confusion whether the diagram you have written is a T channel or S channel without mentioning your, if you do not mention the time. So this is important that you should mention the time. Okay. Of course otherwise you can just mention this is T channel or S channel, but it is always safer to mention the time direction. Okay. Okay. Now what about other process? You can think of another process, nucleon bar scattering. So earlier we have taken psi to psi, but now let us consider psi bar to psi bar. So in this case the diagrams would be, you can think of a diagram to be like this. So again the time is like this. So we have an S channel, okay. Okay. Now the momentum directions you have to be careful here, both of them are incoming to or okay. Now but because this is an antiparticle, you have antinucleons, this is nucleon bar, so this is antinucleon. Okay. Because it is an antinucleon, you have a direction which is opposite on the Feynman incoming Feynman charge, but on the Feynman line essentially, but it is opposite compared to the incoming particle line. So this is an antiparticle. So there is P1 and P2, but the momenta are incoming. See, these two momenta get added up here, and in this square, Q square is equal to P1 plus P2 square. Then you have P1 prime, P2 prime, and again you can ask the question, okay, P1 prime, P2 prime. Okay. So this is a particle and this is an antiparticle. So you have, for the first time we are seeing one S channel process. Is there any other example you can think about? So is there any diagram else which we other diagram you can have? You can also have another diagram in which a particle comes in, goes out, and then an antiparticle comes in, goes out, but they exchange the scalar. Okay, exchange. This is the T channel. So again same thing. So here incoming momentum P1, P2. So you have P1 prime, P2 prime. So this momenta would be P1 prime minus P1 whole square essentially. So, this will be a T channel process which will also exchange the moment, and now you can write the amplitude essentially. So, this amplitude you see it is quite is different compared to the amplitude of psi psi. Okay. Psi psi is just the amplitude of nucleon-nucleon scattering, whereas nucleon-antinucleon scattering is different essentially. Okay, you have different momenta conservation momenta which are allowed. Essentially you have the S channel and the T channel process. So, in the other case you only have the T channel and the U channel process, and it will have different kinematical distributions and so on. So, essentially. Now, let me ask you this question: is meson amplitude is a scattering? Phi phi to phi phi possible. So far we have seen dominantly what phi is acting is like a mediator. Okay. Phi is acting like a mediator of force, essentially it is the mediator of the Yukawa force. It has a mass which is mu, which is like a mediator of the Yukawa force most of the time. Of course, you can think of one process in which you have the phi's also coming out essentially. So, you have phi phi bar psi psi bar going into phi phi. Okay. Psi psi bar going into phi phi, they are external particles, but most of the time they are meaning mediators of this force. So, in this case is a process in which does the mediator can become the external particles such that the fermions, the nucleons itself can mediate the force between the pions. That is the basic question we are asking essentially. Now, the nature of the Yukawa interaction is like this. So, it is the L interaction structure which is governed by, as we mentioned, is governed by the Lorentz invariance and meaning the dimension of the term and so on. So, it only has one phi and two psi's essentially, it only has one phi and two psi's because of the mass dimension and everything. So, at the leading order in Feynman diagrams, at the leading order you cannot think of one phi phi scattering, but directly phi to phi scattering, because okay. So, let us try to build a diagram like this. So, at every phi you have two things. Okay. So, at every phi you have two. Okay. So, you have two phi's, and you can replicate the same thing here also. So, the phi pion scattering, pion to pion scattering through the mediation of the nucleons, but now this process is no longer leading order. Why do you say that? Because at what order in coupling constant this is? In the earlier amplitudes, all these amplitudes are all at I y square. Okay. This amplitude is also at I y square times something. Okay. So, this is also I y square times something essentially. Okay. So, there is an I y square times something. So, here also we have explicitly seen it goes as I y square. Okay. But here how many y's you have? You have a y here, y here, y here, here at the leading order in amplitude okay, loading in coupling constant essentially. Okay. What I mean leading order? The leading order diagram of phi phi scattering appears at these diagrams are called higher order corrections, one loop diagrams. These diagrams are called one loop diagrams, and they go as I y power 4 times something. We will come to the complications plus some complications. We will come to these complications soon essentially. So, but then for the phi phi to phi phi scattering cross section, essentially at the leading order it appears at lambda power y or lambda whatever, meaning y power 4. So, this is a higher order compared to the other process. So, in which psi psi 2, okay, it appears in higher order in coupling constant, it orders 2 orders of more coupling constant compared to psi psi to psi psi. Okay. This is important to note, and this means that these diagrams are some special diagrams, these are called one loop diagrams, and we will continue to see them, and they have some complications associated with the momentum integration essentially. So, they have some complications associated with the momentum integration, and this we will continue to see in later on in one of these lectures. We will see essentially as we move away from tree level process. So, all these other processes are called tree level processes. As we move away from the tree level process, in the coming lectures I mention the complications associated with it and how to solve them essentially and how they are solved. Okay. So, let me stop here and then I will continue in the next lecture. Okay. Thank you very much.